Welcome to our first help video on 5-11, the Unit 5 test. This test is of great importance because we need to understand the concepts, all of the concepts in Unit 5, in order to best understand virtually everything we talk about for the rest of the year. So watch these help videos carefully. If you're still confused on any of the things that are discussed on the videos, please don't hesitate to get help. Help is available. Email me or contact me in class and we can go over anything that the help videos didn't help you with. Here we go. Questions 1 and 2 on the first page. We have a diagram of atom A and atom B. And in this diagram, we can see that A is bigger than B. What can we learn from that? Well, here we go. Number 1, assume both atom A and B are in the same period, which is a horizontal row on the periodic table of elements, also called an energy level or shell. Which one's the metal? Which one's more likely the metal? Well, we have to think about what happens to the atomic radius as we move left to right through a period. We have to look and see what happens as we move left to right through a period. As we move left to right, the atoms get smaller on a given energy level or period. Left to right, they get smaller. Why is that? Well, left to right, we're not adding on levels, but we are adding protons into the nucleus. So the nuclear charge gets stronger as we move left to right. The nucleus has the protons in it. The protons are what pull the electrons in more closely. So as we move left to right, the atoms continually have more than one additional protons in them, which will cause them to pull the negative electrons in more closely. The positive protons attract the negative electrons. When we look at the periodic table, we already know that the metals are on the left and the nonmetals are on the right. And now we know something about their size. So when we look at a periodic table, such as the one right here, the metals are on the left side. We have the stair-step line running right here. Aluminum's a metal, zinc, copper, nickel, cobalt, iron. These are all metals on the left side. The right side, up here in the upper right-hand corner, these are the nonmetals, and the ones that are part metal, which we call semi-metals or metalloids, are right between them. So the metals are on the left side, the nonmetals are on the right, for a respective horizontal row, which we call a period, or energy level. The atoms get smaller as we move left to right. So the metals would be bigger than the nonmetals on their respective row. So when we go back to question number 1 here, atom A is definitely the one that's more likely the metal. One of the diagrams above, question number 2, is the sodium atom, and the other one is the sodium ion. The sodium ion is +1, and it has lost 1 electron. So which one is more likely to be the sodium ion? Atom A or atom B? What happens when we remove electrons from an atom? Is the resulting ion smaller or bigger? Is the cation, the positive ion, smaller and bigger? Well, the cation is smaller. As we pull electrons off, they keep getting smaller and smaller. So here's our neutral atom. We pull an electron off, it gets smaller. Second ionization energy is the energy it takes to pull a second electron off. It gets smaller. We go to pull a third electron off, and it's going to get smaller still. Why do they get smaller as electrons are removed? It's because the nuclear force is now having to pull on fewer electrons, so it can pull them in more closely. So letter B, that diagram would be the positive ion if A was the neutral atom. It's different than anions. When you add electrons to an atom to form an anion or a negative ion, they get bigger. All right. Let's continue on. Okay, questions 3 through 6 are dealing with these diagrams right here. Here's an orbital notation of an element. Here's another orbital notation of an element. Now on these orbital notations, they left off the numbers above the boxes. Remember, we like to put the numbers above the boxes. That's the third number. Third quantum number called the magnetic quantum number. We put it above the boxes. Each of these boxes is an orbital. All right, first one. Before we even start, it's smart to figure out who these things are. Couple quick ways to do it. We could add up all the electrons. 2 and 6 is 10, and 2 is 12, and 6 is 18, and 2 is 20, and 5 is 25. So what element would have 25 electrons? The same one that would start with 25 protons. That would be manganese. Manganese is atomic number 25. So diagram A is manganese. Who's diagram B? Diagram B, let's count the electrons. 2 and 2 and 6 is 10, and 2 is 12, and 6 is 18. This one has 19. If we look on a periodic table, potassium's the one that has 19. You need to have a periodic table out when you do these kind of things. If we look at a periodic table of elements, we would find out potassium's number 19, manganese is number 25. Potassium's 19, manganese is number 25. All right, back to our questions. We've got the two diagrams. Who does diagram A represent? Manganese, there's 25 electrons. Who does diagram B represent? Potassium, it has 19 electrons. And we were told that these are not ions. They are neutral atoms. Which diagram has a larger radius? Well, we would find potassium and manganese are in the same row, which we call a period. There's potassium, there's manganese. They are in the same horizontal row. What happens to the atomic radii as we move left to right? They get smaller. Manganese's radius is 161, potassium's 243. Why do they get smaller left to right? Well, left to right, we're not adding a level. That happens when you go top to bottom. Every time you go down another level, you're adding on another row. Here, we're not adding on rows. We're only adding on protons. Manganese has 25 protons pulling on the electrons. Potassium only has 19. 25 protons can pull the electrons in more closely. Therefore, diagram A would actually be the smaller, or which one has the larger radius? Diagram B would have the larger radius. So we can clearly see now that diagram B would have the larger radius because it only has 19 protons pulling on the electrons. Diagram A had 25 protons pulling on the electrons. Diagram B's radius is 243. Manganese's radius is 161. It would definitely, diagram B would have the larger radius. Which one would have the greater ionization energy? The smaller one would. So for number 6, why would diagram A, manganese, have a higher ionization energy? The answer is it's smaller. Ionization energy is how much energy it takes to rip an electron off. So if we try to rip an electron off out of manganese, it's smaller. So that electron in the S sublevel, we would be pulling one out of the 4s. That 4s is smaller and pulled in more closely because of the increased number of protons. So if we look up their actual ionization energies, manganese's ionization energy is 710. Potassium's ionization energy is 420. A lot more energy to pull one out of manganese. All right, that takes care of 5 and 6. Let's move on to number 7. Place these elements in increasing smallest to largest. So they want us to put argon, lead, sulfur, helium, and silicon in order of smallest one first, largest one second. Well, what do we know about the atomic radius? Going left to right, they get smaller. Right to left, they would get bigger. Why? On a given row, we see that in the general trend is that they get smaller on a given row, because on a given row, we're adding protons to the nucleus. We're not adding levels on. You can only add a level when you move down a level. So what we are adding is the number of protons to the nucleus, which will pull them in more closely. Top to bottom, what happens to the radius? They get bigger. Why? Every time we go down another row or period, we're adding on another level, another story to the building. So the first row has 1 story, second row has 2 stories, third row has 3 stories, fourth row has 4 stories, and so on. So they get bigger going down. They get smaller going to the right. So the smallest ones would be in the upper right-hand corner. So in fact, on our list, we have helium. Helium certainly would be the smallest atom in that list. There's helium up here. Here's the atomic radii. Helium is only 31, so it would be the smallest. The next element on the list that we deal with, we've got helium. It should be first. So in our answers, we could get rid of really any answer that doesn't have helium first. So this answer is going to definitely be out because helium's not first. This answer is definitely out because helium's not first. But C and D both have helium first. Now, where do we go? Well, our next element that we have on there, which one's closest to helium on this list? We look down, argon is 2 rows below helium, and it's to the right. So the next smallest would be argon. Then what happens to the size if we're looking at the next ones? We've got sulfur to deal with, we've got silicon to deal with, and we've got lead right here at the bottom to deal with. Well, helium's the smallest, argon would be the second smallest because it's to the right of these other 3 elements. So when you're to the right, the ones that are the highest and to the right are going to be the smallest. So we go from argon. Sulfur's to the left of argon. They get smaller going left to right. That means sulfur is bigger. Silicon is to the left of sulfur. They get smaller left to right. So that means silicon must be bigger. And lead is 1, 2, 3 stories below silicon. So lead is definitely going to be the largest. So our order then would go helium, argon, sulfur, silicon, lead. That's letter D. The next question's on the shielding effect. Which of these elements would have the highest or greatest shielding effect? What is the shielding effect? The shielding effect, and you can click on there. They had a little link if you forgot what shielding effect was. But shielding effect is sometimes called the screening effect. And that's where the inside levels of an atom get in the way of the nucleus pulling on the outermost levels. So when an atom has a lot of inner levels, those inner levels tend to shield or screen the pull of the nucleus on the outermost electrons. So atoms that are large are going to have their outermost electron being held even more loosely due to the inner levels getting in the way. As it says here, the shielding effect describes the decrease in attraction between an electron on the nucleus for atoms that have more than one shell or inner level. The more electron levels or shells it has on the inside, the greater the shielding effect. So big atoms are even bigger than you would expect. Big atoms are even easier to strip an electron from than you would expect. Bigger atoms have trouble pulling electrons to them, so their electronegativities would be less due to the shielding effect. And the electron affinity would also decrease due to the shielding effect, because electron affinity is the measure of how much an atom can accept another electron. And if it's big, it has trouble accepting it. So really, they're asking who has the most energy levels. Lithium's on the second level of the periodic table. So it only has 2 levels, 1 inner level. Sodium has 2 inner levels, 3 total levels. Potassium has 4 total levels, 3 inner levels. Rubidium has 5 total levels, 4 inner levels. Cesium has 6 total levels, or shells. So it would have 5 levels getting in the way. So when we're looking at it, here we go. Lithium is there on the second row. Sodium's there, potassium's there, rubidium's there. Cesium has 1, 2, 3, 4, 5 inner levels of electrons that block the pull of the nucleus on their outermost electron. Letter E, cesium, has the greatest shielding effect. The next video we'll pick up with question 9.